There are several ways for us to examine the graphs of tangent and cotangent functions. For tangent, we're going to begin the discussion by using the information we already have about sine and cosine. And we're going to think of tangent in the identity form. That is, tangent is sine over cosine. Take a look at this pattern. For values of x that are at these values that were so very important for sine and cosine, I'm going to calculate sine x and cosine x and then the fraction sine x over cosine x, which is tangent x. All right, so now we know these to be the important values for sine and cosine. The sine curve we know starts at 0. You see, that's all there is to all of these values is where they start, top of the amplitude, x-intercepts, bottom of the amplitude, and that kind of thing. So we imagine the sine curve. At 0, we start the sine pattern at the origin. At pi over 2, we go to the top of the amplitude. At pi, we go back to the intercept. At 3 pi over 2, we're at the bottom of the amplitude at -1. And at 2 pi, we're back to 0. So we have one complete cycle then of the sine curve. For the cosine curve, we know we start at the top of the amplitude and end up there as well. So at 0, we're at the top of the amplitude at 1. And then at pi over 2, we're at the intercept. At pi, we're at the bottom of the amplitude. At 3 pi over 2, we're back to the intercept. And at 2 pi, we're at the top of the amplitude. Okay, now, to calculate the tangent based on this information, all we do is make fractions out of these values. So it's sine x over cosine x. So for the first value, let's see, it's 0 over 1. 0 over 1, that's 0. For the next value, it would be 1 over 0. Uh-oh, 1 over 0. 0 in a denominator means we have an undefined value. So the situation is undefined at pi over 2. All right, now, what about the next one? We have sine over cosine now. So we have 0 over -1, that's 0. Then -1 over 0, uh-oh, another undefined situation. And then 0 over 1, which is 0. Wow, we have these points to plot. Not much information, is it? Well, we're going to examine this from another point of view here in just a second, but let me go ahead and plot these points. Now, you know with undefined values of a function that a lot of times we have asymptotes involved, and that's true here. Now, it's not always true that we have asymptotes involved when we have an undefined situation, but sometimes we do, many times we do, and in this case we do. So as I go through and plot points, at 0, we go to 0. At pi over 2, it says over here from the chart that I have an undefined situation and we end up having an asymptote. At pi, well, let me look back. Oh, it's 0. And at 3 pi over 2, another asymptote. And at 2 pi, we're back to 0. All right, let's make the discovery of what happens in these various intervals by looking at the unit circle. Now we're going to start with we'd like information about the behavior of the graph in the interval from 0 to pi over 2. Now that interval corresponds with, on the unit circle, the first quadrant. You see, the first quadrant is just values for x that are between 0 and pi over 2. And do understand here that, well, several things to understand. First of all, we're taking this approach. We're using this study and analysis and comparison with the unit circle and our number line here just for a greater understanding of trigonometry and an appreciation of trigonometry. That's one thing. We don't have to do it this way. I could just show you the graph on the graphing calculator and be done with it and show you aspects of the graph and how it changes according to changes in the equation. And that would be pretty easy. But you wouldn't have the depth of knowledge that you're going to have by going through this idea. And I suggest that you go through this kind of study by yourself, that you can actually do this alone from time to time to get a better understanding of the dynamics of the graph of a function such as this one. Okay, now let's understand this about the situation, that as I make right triangles in this unit circle, and I'm taking the right triangle approach here rather than points on the unit circle which have coordinates and all of that kind of thing, because I think the right triangle approach is one that's very hands-on. We can see values very easily like that. So we are thinking either in terms of an angle in degrees, changing from 0 to 90 degrees, but gee, our coordinate plane is labeled with radian measure, so 0, pi over 2, or 90 degrees. You see 180 degrees, 270, and so on. We could do it in degrees if we want to. Or we could think of the angle changing in terms of radians. Or we could think of the length of the arc changing. If this is a unit circle, then we can think of the length of the arc changing from 0 to 2 pi. Excuse me, from 0 to pi over 2. Okay, so all of those things are in play here. Now, when our triangle is located in the first quadrant, and when that angle is very small, or when this arc length is very tiny, then we get a fraction opposite over adjacent from the standpoint of this angle of, let's see, the opposite side over this side. Now the opposite side, when that angle is really small, is a really tiny number. So, and actually at 0 degrees it is 0, and we know that already from the point that we plotted up here. Okay, but what happens as we just kind of get a small angle here that has some value? Well, it turns out that we have a relatively small number over a number that's near 1. Well, that's just tiny fraction. So we have small numbers here for the tangent when we're talking about an angle which is pretty little. And remember, we're just talking about a y over x idea here when we're thinking about this. This is the y, there's the x. And the x only goes up to right there. Okay, now, somewhere right in the middle here, like roughly right here, for a 45-degree angle or an angle of pi over 4, in that circumstance, the y distance and the x distance are exactly the same. You see, so we have some number for y, some number for x, they're exactly the same number, and therefore the fraction becomes 1. So at pi over 4, the tangent of x, the tangent of the real number we're talking about, or the angle, turns out to be 1. So somewhere right in the middle here at pi over 4, that's right there, we're up at 1. Okay. Now, I'm suspecting here that I know that the graph goes from this point to this point, and I'm seeing that this is an asymptote, so the graph is going to get really close. Let's see why it gets close and goes upward, goes in the positive direction without bound. Let's look at that situation down here. You see, if as our triangle, the length of the arc moves near this pi over 2 point, then the fraction becomes one of y nearing 1 over x nearing 0. So that x value, that denominator, is becoming very, very tiny. And the tinier it gets, the more times it goes into that numerator, even though the numerator is pretty small. X is getting really, really little, and it'll go into that y value more and more times. And the closer it gets to the pi over 2 mark, the smaller x gets, and the more times it goes into the numerator, and the bigger this fraction becomes. And that's why it goes upward without bound. And the situation then looks like this. It's kind of like that. Now it continues over here, and we'll consider that in a little bit. But let's talk about what happens in the next interval. Now the next interval, the next important region, is between pi over 2 and pi. And that's this region of the coordinate plane. But that region of the coordinate plane can be analyzed using the unit circle in the second quadrant, because after all, we're talking about x values that are between pi over 2 and pi. And on the unit circle, this is pi over 2, and that's pi. Whether we're thinking about length of arc or size of angle, it's pi over 2 to pi. Okay, as soon as we jump over this mark at pi over 2, and I'll just label it here, as soon as we jump over that mark, here's what happens. Now, we have this y over x idea, so we have y and x. Now, the x has suddenly become negative. You see, we're on the south side of our horizontal number line here. So x is negative, y is positive, and so we have a fraction which is going to be negative. And because we're really, really close here to pi over 2, we're just a little above pi over 2, that x distance is really tiny. And tiny goes into a fixed number many, many times the same way it did on the other side. So we have a really big negative value coming into play right in this region of our unit circle, and therefore in this region of our coordinate plane we have really, really large negative values, and so the graph is going to come up like this. Now what happens? Well, the next critical spot turns out to be right here, where the right triangle turns out to have an opposite side the same as the adjacent side. And so we have a fraction which becomes 1. And so that happens right in between pi over 2 and pi. So right in between pi over 2 and pi, in this spot right here, we have a negative 1 value for our function. And that turns out to be right here. And now the graph comes back, and it comes back to that point. Okay. Now we've actually gone through one cycle for the tangent curve. I'm not drawing this anatomically correct. Let me try to do this again a little bit better. The way it goes is like this. Does more of this kind of thing, as we'll see more of later when we hit the calculator business. Okay, so we've gone through one cycle, and I kind of know it's one cycle because, well, not only because I've seen it before, but because we are back at 0. We're coming up from 0, and it's like we're coming up from 0 right here. You know, it's the same idea. So the behavior to the right of pi is going to be the same as to the right of 0. Right in this region, same kind of behavior right here. And we can analyze it in precisely the same way. That is, we can think to ourselves, well, as the triangle gets kind of close to pi over here, then what's going to happen to the fraction? You see, what's going to happen to the y over x? Well, the y is getting really tiny. It's approaching 0 here. X is approaching 1, but y is approaching 0. That's the numerator. It's approaching 0. So that number is getting very, very small. So as we get very close to pi, it gets very small and actually arrives at 0 right here. And then in the third quadrant, which would be the pi to 3 pi over 2, this region right here, we would analyze that, and both the x and y are negative, and that's why the fraction becomes positive, and so we jump up into the positive region of the coordinate plane, and all of those kinds of dynamics take place. Okay, the important matter here is to notice that one complete cycle of the tangent curve occurs in an interval that is pi in length. So between 0 and pi, we have a complete cycle. Now, the cycle seems to be broken up right here in looking at it in this particular region. It's easier to see the whole curve by looking at a pi length interval somewhere like this, between the asymptotes, you see. And the most convenient place to look at it is really right here, and to think of it like, okay, here's pi over 2. Let's go a distance of negative pi over 2. You see, along the number line. And now we can do this kind of thing. And we have an asymptote here. So we have our period that is pi in length right here, and that period is straddling the origin, and that's the way that we want to look at the situation. Okay, let's think about domain and range. Now, for domain, if we're thinking domain in terms of the way that we looked at domain in the past, then we would think, well, that's the acceptable replacements for x. That's the values of x that make sense. And all values of x make sense. They appear on the graph except those values that are at the asymptotes. You see, x can't take on those values because it causes the fraction for tangent to be undefined. Okay, so we say then that the domain for y equals tangent x would be all real numbers except x equals pi over 2 and x equals pi over 2 plus or minus pi. Now it's plus or minus pi because pi is the length of the interval, you see, over which we have a period. And at the end of the period we have another asymptote, and then another, and another, and another, and another, forevermore. So it's pi over 2 plus or minus pi, pi over 2 plus or minus 2 pi, pi over 2 plus or minus 3 pi, and so on. But more generally, we simply say that the domain would be, we just list the exceptions usually for the domain. We would say x is not equal to pi over 2 plus n times pi, where n is an integer. That's the simplest way to do it. Okay, the range, the y values that are on the graph, well, that would be all real numbers. And we know that we have a period of pi, and that period we think of the basic pi length interval over which this tangent curve occurs is straddling that, that origin. All right, let's look at a graph. Now, we're going to look at the graph of a function that's not just basic. We're going to add a couple of nuances here. And the various nuances will have the same effects on the graph that they have had before. That is, if we're thinking about y equals a tangent bx, the a value will cause a stretching or compression of the graph up and down. That is, if a is greater than 1 or less than negative 1, then we have a situation like this. Now, I'm just going to kind of sketch it like this. If a is greater than 1, and let's say a lot greater than 1, then the graph would almost be like this. It just kind of stretches things out this way. Now, if a is between 0 and 1, like 0.2 or something like that, then the graph will have more of a behavior like this. It'll come in and make a rather dramatic turn here at the origin. Okay, so that's the idea. Now, the negative idea, if a is negative, then it will tend to flip this graph over. So it'll have this kind of effect. Now, if this is the basic graph, a negative 1 value for a would just cause the graph to look like this. You see, and if that negative value were really large in the negative sense, then it would kind of stretch it out like it did up here. And if it were small in the negative sense, like negative 0.3 or something like that, then it would cause it to be a little squattier, kind of like that. Okay, so that's the effect of a, and it's kind of what we expected from our study before. The b value behaves in much the same way that the b value in this position did with sine and cosine. And to calculate the period of the equation that we're dealing with, we just take the normal period and divide by that coefficient. And that's what we did before. It was 2 pi over b before. It's just pi over b here because the normal period is pi. Okay, so to graph something like y equals 1/2 tangent x over 2, what we might do first is rewrite the x over 2 as 1/2 x so we can see the distinct coefficient here in order to make a calculation for the period. Now the period is pi over b, the b value is 1/2, pi over 1/2 is 2 pi. So our full period is 2 pi. Now here's how we would go about stretching the graph, or excuse me, sketching the graph. I don't mean stretching the graph. We would do this. We would start with, let me move over just a bit. Now, if the period is 2 pi, and we know that the basic period, the one that we kind of start our thinking with, straddles the origin, then what we'll do is we'll split that period of 2 pi into two parts right here at the origin. So we'll have half of it on this side, half over here. So we'll identify pi on this side, negative pi on this side. And that's a full period of 2 pi. And we have asymptotes here and here. Okay, and now it's just a matter of drawing the graph, and if I'm going to try to draw this sort of correctly, and I could go into and making a table of values, I could use my calculator to calculate exact amounts for that table and so forth, but just sketching this thing, a 1/2 coefficient here will just cause that graph to come down and make a more dramatic turn. So I'm thinking that the graph will have this kind of behavior. You see, it'll look roughly like this. Now, this situation continues forevermore in both directions. So what we would do is come out here. If we want one more cycle on this side, that's fine. We just come over here and extend our x-axis. And we want to go a distance of, well, it's the distance for the period. It's a 2 pi distance. So we go 2 pi over here, add 2 pi to pi, and we get to 3 pi. And right in the middle of 3, and that's where the asymptote is. And right in the middle between pi and 3 pi is 2 pi. And that's where we're going to have a crossing. So the graph then will look like this. Now it'll have the same behavior over here as it did in the first one. And then we could continue this, as I say, in both directions. We're going to use the same technique in examining the graph of y equals cotangent x as we did with y equals tangent x. But now that we have all of the information about the tangent function and its graph, this will be pretty easy. We go through the same kind of thought process where we take values of x and we evaluate sine x and cosine x for those important values, and then we calculate the fraction cosine x over sine x. Now remember, this is just the reciprocal of tangent, and we can use that idea along the way here whenever we see fit. Well, at any rate, with the cosine over sine, let's see, cosine over sine, so 1 over 0, that's undefined. 0 over 1, that's 0. Negative 1 over 0, that's undefined. 0 over negative 1, that's 0. 1 over 0, undefined. We know what happens at these undefined spots. Let's identify them on the coordinate plane. So we have an undefined situation at 0. That means we have a vertical asymptote here. And again at pi, and again at 2 pi. All right, so now the trick is to discover how the graph behaves between the asymptotes. Well, let's see, at pi over 2 and at 3 pi over 2, we found the value of the function to be 0. All right, so we know the graph goes through here. Now recall that the basic behavior of the tangent function was, or the graph of the tangent function was that it kind of increased from left to right. You see, it had this increasing thing. Now we're seeing kind of a shift of our fundamental period here. We're seeing a period that's the same length. You know, we have a pi length period over which the graph is occurring, but it's kind of shifted on the coordinate plane. It's a little more normal from our experience of sine and cosine. It starts at 0 and ends at a particular point, and that point is at pi. Okay, so now let's evaluate the situation in this area. Well, I think the easiest situations to evaluate are those at the 45-degree angle spots and the reference of 45-degree angles. You recall that with the tangent function here at pi over 4, you see at pi over 4, the 45-degree angle, we had a 1 over 1 situation. Well, here this is the reciprocal of 1 over 1, so it's still 1 over 1. So when x is pi over 4, cotangent x is 1. So this goes to 1. And at, let's see, then we have another situation like that in the second quadrant. Now, I say second quadrant, and I'm thinking second quadrant because this is between pi over 2 and pi. And we could definitely look down here at our unit circle to make the evaluation. You see, we could make the evaluation for the pi over 4 like this. We could say, well, somewhere along this unit circle, we have a spot that's pi over 4, and at pi over 4, we know that the x and y distances are the same, and so for cotangent, it is x over y, remember, so it's x over y, but they're the same, and therefore we have 1. Okay, so positive 1. Then a similar thing happens here at, right in the middle of this situation. Let's see, it's between pi over 2 and pi. It is 3/4 pi, or 3 pi over 4. You see, so here, our reference angle is here, and our reference triangle is here, and again we have this x over y idea, except x is negative. You see, so we have negative 1 for the value of the cotangent at that point. So, gee, here at 3 pi over 4, we have negative 1, And it's looking like the graph is going like this. And indeed it does. And we could examine the situation about what's happening as we get really close to 0 over here and really close to pi on the left side and really close to pi on the right side and all of that kind of thing like we did before. But we know how to do that now, I think. And I'll just tell you that the graph has this kind of behavior. Very similar to the tangent function, except, and very important, a very important exception, is that the graph continually decreases within an interval, whereas the tangent function continually increased in its interval of its period. And again, we have a repetition of that behavior in the next interval, and we have that repetition over here as well, of course. Okay. With that in mind, now we can talk about domain and range and so forth. And the domain, the acceptable replacements for x, would be all of the x values, all of the real numbers, except for those real numbers that will cause an asymptote to occur, will cause the function to be undefined. And that occurs at 0 and at pi and at 2 pi, and every pi at the end of every pi-lengthed interval. So we can say then that the domain for y equals cotangent x would be all real numbers except some, or we can simply say that x is not equal to pi plus n times pi, where n is an integer. The range is all real numbers because the graph goes out of sight up and down, and the period is pi, as it was with tangent. Now, to construct graphs, we need information about the stretching and compression and how the period may change from time to time. And it's exactly the same as we would expect. It's exactly the same as it was with the tangent function. If we have y as a cotangent bx, then the period is pi over b, as it was before, and all of the things, all of the aspects of a will affect cotangent just the same way that it did tangent. So if we're talking about y equals cotangent 2x, then it's a matter of identifying period and thinking about a. Well, a is 1, so it's kind of a normal curve. Now that normal curve, remember, is one which tends to fall throughout the period rather than rise, as was the case with tangent. So let's just keep that in mind. So for a period of pi over b, the b value is 2, so it's pi over 2. So all we have to do is identify the position of pi over 2. You see, and that's the period length. The period starts at 0. So in 0 to pi over 2, we have one complete cycle of the graph. And all we need to do is realize that the graph has an intercept right in the middle of the period and that it tends to fall. So we have that. And let's just go over another cycle over here. Double pi over 2, and we have pi. So we have another asymptote at pi, and we have another curve, and back this way I could do another one. I guess I'm doing this just because I like to. Okay, and continuing on in both directions forevermore. This one is a little more complicated. We have y equals negative 1/2 for the a value, cotangent x over 3. I would rewrite the distinct coefficient of x here as 1/3 x. Now that way we can identify the length of the period. So it's pi over b, or pi over 1/3, which is 3 pi. All right, now we'll talk about the effect of a in just a minute. But to set up the graph, we do this. We just say, okay, our cotangent curve is basically starting here. And by the way, we're not talking about phase shifts here just yet. We're going to save that for another time. And there are such things as phase shifts here with tangent and cotangent, but we're just not discussing them right here at the moment. Okay, we're starting here at 0 then, makes it real easy. We go over to 3 pi. Well, let's say that 3 pi is right here. And we have another asymptote. You see, and over here at 6 pi we have another one. Now, how does the graph behave? Well, we know that the graph is going to go through going to have an x-intercept right in between the period. Okay, that much we kind of know. But what about well, first of all, the 1/2 idea. Now, the 1/2 idea causes the graph to just kind of be compressed a little bit in this direction. So if we were talking about the normal graph, and just with 1/2, without the minus, it would look kind of like this. Now I'm just going to exaggerate the compression here, so it looks something like that in both of these intervals, of course. Okay, so I'd do that. Now, the negative, though, causes the graph to flip over. You see, now imagine this graph just flipping over on the coordinate plane, and so it would have a behavior like this. You see, and like this in this interval. Looks a lot like the tangent curve, but that's kind of naturally going to happen. It happened with sine and cosine. It's going to happen here with tangent and cotangent, as we would probably expect. Well, let's look at some of the aspects of the graphs of tangent and cotangent using the graphing calculator. Let's start our investigation with y equals tangent x. And in the window settings, notice that for the x scale, I have set the scale at pi over 2. Well, the graph of tangent x has this appearance, as we would expect. Notice that we seem to have a vertical asymptote coming up here at pi over 2. This really is not a vertical asymptote that the calculator is drawing. It serves that purpose for us here, but it's not actually the asymptote. Actually, the calculator is connecting a point that's just to the left of that vertical line up here with a point that is just to the right of the vertical line over here. The calculator doesn't know that these points do not need to be connected, but the connection serves the purpose of that vertical asymptote, so we'll just leave it alone. And we could remove these vertical lines by resetting the calculator in a dot mode rather than a connected mode, but I think they serve a rather nice purpose for us. Well, let's look at a related graph. Let's just take 0.5 of this same graph, 0.5 tangent x, and see the two graphs together. And as we might expect, this graph of 0.5 tangent x is a little squattier than the other graph. And that's because the vertical distances for tangent x, like this vertical distance for tangent x, we're just taking half of it for 0.5 tangent x. So this distance right here is just half of the corresponding distance at that same x value. So that's the whole idea with that. Let's go back and clear these two and look at cotangent functions. Now cotangent, since cotangent doesn't appear as a button on our calculator, we have to be a little creative with the way that we enter this. So we enter this as 1 over tangent x. We know that they are the tangent x and cotangent x are reciprocals of one another, and so here is the way we enter cotangent x, and here is its graph. Now the little double or thick line here at the y-axis is occurring because of the connection, you see, of a point way down here off of the graph to a point way up here off the graph on either side of that axis. So we kind of get a double line there. But that's okay. It kind of serves a nice purpose of telling us where the y-axis is. And we'll notice that the graph looks kind of similar to the tangent graph. It's just kind of flipped over and shifted a little bit left and right. And that's kind of what we expected. Let's do something here. Let's go back to y equals, and let me make this graph with a thick line. Now I'm going to press enter here until I arrive at the thick line. Here it is, and the graph then will have this thick line appearance. Now in using this, I can now compare this with the tangent graph. I'd like to go back and just enter tangent x, and its graph then will make an appearance. Well, the coordinate plane looks particularly convoluted here because of all these vertical lines, but just understand that the tangent graph is the one that's coming up and it's regular dotted, and the heavy line is the cotangent of x. All right, let's try to manipulate the tangent graph, actually the function, and cause it to look like the cotangent. Now, one thing we can do, we need to get it to flip over, and we can do that by just tacking on a negative sign here. You see, and I should have pressed insert, and I didn't, but it's the negative of tangent x, and I'll close this. And now the graph will simply flip over. And here's cotangent coming up first. Now here is the tangent coming up. Now we're kind of getting somewhere. We want to get a match if we can. We want to match these up. I want to get this graph to overlay that one. So all I need to do is arrive at a shift. Now I'm noticing here that I've got a shift distance of pi over 2. So all I need to do is go back here, and right here I'm going to say minus pi over 2. So pi over 2, close parenthesis, and we should get a consistent kind of graph. Now if we get a consistent graph, the unfortunate thing is that when that little dotted line overlays the thick line, we're not going to see any difference. We'll only see a difference if we do something like trace and jump to the other graph. For example, here I'm at, well, it's telling us up at the top that I'm on y1, and if I jump to y2, you see I'm at the same spot, just about. You see and I can see the xy components at the bottom are not changing when I jump from one graph to the other. So these are absolutely consistent graphs. Well, let's stop this playing around and let's go to something that we've looked at a moment ago. Let's enter the equation that we had on the board just a bit ago. It was negative 1/2 cotangent x over 3, so that's negative 0.5. Now, I want cotangent, and we know that to be 1 over tangent, so I'll open a parenthesis and go 1 divided by tangent, and I want x over 3, so x divided by 3, close, close, and here is the graph. Now we're using the same settings that we had on board just a few moments ago, and we're noticing that the entire graph is not even appearing in our viewing window, and that's because we said that this equation had and the graph had a period of 3 pi. And here we have pi over 2, and this is pi, and here is 3 pi over 2 and 2 pi. Well, we have to go out a bit further to see an entire period. We can accommodate that rather easily. If I go to the window settings and I set an x minimum of, well, let's see, it's 0 to 3 pi that I want. I'd like a little bit of room on either side, so I'll set this at negative 1. And look at the way I can set my x maximum. I can set this as 3 pi and then plus 1, just 3 pi plus 1, just 1 over to the right of the period. Now my x scale is still at pi over 2, and incidentally, when I cursor down, the calculator is making the calculation in terms of decimals for the x maximum. Let's make the x scale, I can make it pi if I want to for this one, and now the graph. You see, I wanted to show you the period in terms of pi. Here's pi, here's 2 pi, here's 3 pi. You see, and this is one entire period. And if I want to change that scale a little bit, I just go back to the window settings, and I can set this as pi over 2 very quickly. And the graph then will give me some significant points here, particularly this intersection point at 3 pi over 2. And occasionally we would want this graph to be exactly anatomically correct. It's pretty close to being by anatomically correct, I mean a square perspective, and we can accomplish that very easily by just pressing number 5 here in the zoom window, in the zoom menu. And this is exactly a square perspective, and so we're not distorting the graph in any way. It looks pretty much the way that it did before. In the window settings, I had negative 3 and 3 for the y minimum and maximums. So that changed just a little bit here for our square perspective. The graphs of secant and cosecant functions can easily be analyzed by thinking of them as the reciprocals of sine and cosine functions. So if we want to analyze the graph of secant x, then we just think of secant x as 1 over cosine x. Yeah, it is important to understand some aspects of reciprocals. For example, the reciprocal of 0 would be, well, let's see, 0 can be thought of as 0 over 1, and the reciprocal would be 1 over 0, but 0 in a denominator means undefined. So that's one important notion. Another is that the reciprocal of small numbers would be big numbers, and the reciprocal of big numbers would be small numbers. I mean, if we take a small number like, oh, let's say 1/10, its reciprocal is 10 over 1. So the reciprocal of that tiny number is a pretty big number. Now, with that in mind, here's how we analyze the graph of secant x. We start with the graph of cosine x. Now, here's cosine x over 2 periods. And, well, let's see, the reciprocal of the values that this graph takes on, you see, throughout this interval. Well, the one value is here at 0, at the intercepts. Well, the reciprocal of 0 is undefined, so we have an undefined value then for the secant function. And let's just go through and identify all of those spots. The reciprocal at 0 here and here and here and here will be undefined, so we have asymptotes there. Now, think about what's happening just to the left of this asymptote. We have values of the cosine curve which are very small positive numbers, and their reciprocals, you see, for this value of x, cosine x is a small positive number. So secant x is going to be the reciprocal of that value, and the reciprocal is going to be a big number. So the reciprocal is going to put a point on the graph way up here. Now, very near 1, where the cosine x is very near 1 and the x value is very near to 0, but the cosine of x is very near 1 but a little bit less than 1, the reciprocal of a little bit less than 1 is a little bit bigger than 1. And so the graph then will come in like this. It almost looks like a reflection of this part of the graph. It kind of looks like it. It's not exactly, because after all, the graph up here is asymptotic, you see, has an asymptotic nature to it. You like that word, asymptotic? I like that. I'm going to use it often. It makes me sound real smart. But anyway, so we have this asymptotic nature of the graph up here, whereas we don't have that right here. We actually go through the vertical asymptote here, and it's not an asymptote for this graph anyway. Okay, now what about in this interval? So in this interval, here's what's happening. We have negative values for the cosine curve, and if we are very near this intercept, then the values for the cosine are very small negative numbers, and their reciprocals are very big negative numbers. So we have values way down here. And when we get to -1, the reciprocal of -1 is -1, so we have this kind of behavior. And then as we get near over here, same idea. You see, the values go down. And as soon as we cross over the asymptote, we get above the x-axis, so we have small positive numbers, and the reciprocals are big positive numbers, and the reciprocal of 1 is 1, and so the graph looks like this. And again, we can just about think about the situation as kind of a reflection within each of these various intervals. So right in this interval, we have a reflective quality, and in this little half interval, if you will, we have this kind of quality. Okay. So we kind of analyze the graphs of secant and cosecant, even the more complicated ones, by thinking of them in this reciprocal kind of fashion. Okay, consider this problem. Looks really complicated. It's y equals 2 cosecant of all of this business. Well, all we do is think about its reciprocal function, the related reciprocal function. Now let's see, the reciprocal of cosecant is sine. Okay, so we write y equals 2 sine of same binomial. And we go through the analysis process for sine. All right, I'd like to be able to identify the phase shift in an algebraic form here. So I'm going to force the factorization of pi over 2 out of this term. So here's what I'll do. I'm going to snag pi over 2 out of this, leaving x, and snag pi over 2 out of that, and it leaves 1. So we have this. Now, we just analyzed the graph as we did before. The amplitude is at the absolute value of 2, which is 2. The period is 2 pi over b, but the b value is pi over 2. So it's 2 pi over 2. That turns out to be 4. The pi's go out here. A little bit of an unusual situation for these graphs. Then we have a phase shift corresponding to this number, but in a direction we don't expect. We see minus 1, so the shift is to the right 1. So phase shift 1 to the right. Now we just march over and we construct the graph according to this information. Now when you start the graphs of these, you can almost start with the same kind of template every time. You just have a coordinate plane and you make some equal marks on your x-axis, and then just have a horizontal dotted line above and below, same distance above and below the x-axis, and that's going to be your amplitude lines. And so when we see that the amplitude is 2, then we'll just mark this as 2 and this is negative 2. All right, now we have a period of 4. So let's see, 1, 2, 3, 4. So this is the interval over which we will have one complete cycle of our graph. But we have a phase shift, and the phase shift is 1 to the right. So we just shift this whole interval 1 to the right. Boom. Now this was 4, and when we go 1 to the right, we end up at 5, and this is where 1 was. So our graph is going to have one complete cycle between 1 and 5. Now notice that we have markings, in the important spots for the sine curve. So we start the sine curve at the intercept. We go to the top of the amplitude. We go back to the intercept. We go to the bottom of the amplitude, and we go back to the intercept. So the graph looks like this. Okay, one cycle. Now we might continue the cycle a little bit in both directions. So certainly we would want to continue the cycle back this way, at least to the origin. So we would continue the cycle back to this spot. And we may need to go back a little bit further in some situations, because in some problems there is a definition for the domain of a particular function. We might want to define this function or graph it from negative 2 pi to 4 pi or something like that. So you have to just extend your graph in either direction, maybe both, to accommodate that. But let's see, to continue the situation, every one of the marks is a significant point graphically. So let's see, at this mark we would go to the top of the amplitude, back to the intercept, bottom of the amplitude, intercept, top of the amplitude, intercept, and I'm out of room here. So we have this kind of thing. Now we're ready to construct the graph of the original function that we wanted the graph of in the first place, and that's that cosecant function. Now to do that, we just think about the reciprocal values that the graph takes on according to the values that sine has taken on. Now first identify the asymptotes, and those will be the reciprocals of the zeros, which will be undefined values. So at the intercepts we have asymptotes. Okay, now we're looking for this reflective quality, if you want to think about it like that. We don't have to go through the full analysis like we did before. It's just that right in this interval, and we're just taking one interval at a time. In this interval, we have this reflection idea, you see, with this lower part of the amplitude, and so the graph is going to look like this. Now, and up here, in this interval, we have a reflection, sort of a reflection of this kind of thing, except we have this asymptotic behavior that's going on. And then over here, same idea. Up here, same idea. Down here, same idea, and so on. Now your teacher may require that you put the sine curve in some kind of dotted fashion so that your continuous line type of graphing illustrates the function that you're trying to graph in the first place. All right, here's another rather interesting situation. we have y equals x over 2 plus this cosine business. And it looks real complicated. And there are actually three techniques that I want to show you for dealing with the graph of this equation. One of them is just a fundamental point plotting method, and you build a table of values by thinking about the x over 2 and the 2 cosine pi x sort of as separate ideas. So I'm going to make a column for x values, and then a column for x over 2 values, and a column for 2 cosine pi x values. Now I'm choosing the values of x because of the situation that's occurring here in this cosine expression. I have pi in place already, and I can take the cosine of items like pi over 2 and 3 pi over 2 and 2 pi and things like that. So I'll let x take on values that will give me values like that I can take the cosine of. So I'll come back over here and let x take on values 0, 1/2, 1, 1.5, and so on. Now 1/2, you see if x is replaced with 1/2, we have becomes pi over 2. You see, and on the cosine curve we know that that situation gives 0. The cosine of pi over 2 is 0, and then 2 times 0 gives 0. That's how this came about. I'm getting ahead of myself a little bit. I started with 0, then I went 1/2, 1, 1.5. And then for x over 2, 0 over 2 is 0, and then 1/2 over 2 is 1/4, and 1 over 2 is 1/2, and so on. All right, and then for this one, I replace with these values of x, and I get some familiar values here, and then 2 times those familiar values give me 2, and then 0, and then -2, and then 0. And now for the y column, all I need to do is add these. So 0 and 2 would be 2. 1/4 and 0 is 1/4. 1/2 with -2, -1.5. 3/4 and 0 is 3/4. Now in developing this scheme, there are some real negatives that go on here. One is that with all of this arithmetic and all of this conversation that we've had, we've only generated 1, 2, 3, 4 points to plot. And certainly we know that this is a pretty curvy graph. That's a straight line, you see, and so the sum of those two is going to be a curvy graph. And to discover the behavior of curvy graphs, we need an awful lot of points to plot. And we're not generating very many right here. Well, to help us along the way with that in using this technique, a lot of times some kind of pattern is developed here for this column and for this column. Not so much the last column. Generally, there's no pattern really that we can follow develops over here. But these will have a pattern probably that will emerge. Now, the pattern for x's is 0, 1/2, 1, 1.5. Oh, I'm increasing by a half each time. So let me continue that pattern. This would be 2, 2.5, and so on. All right, then in this column, notice what's happening. 0, 1/4, 1/2, 3/4. You see, I'm increasing by 1/4 every time. So 3/4 and 1/4, you see, would be 1. And then 1 and 1/4, and so on. All right, and here, this is the pattern of the cosine curve. It's top of the amplitude 0, bottom of the amplitude 0. Next thing in line would be the top of the amplitude, and then 0, you see, and so on. Well, and then we would, of course, add these. We have 1 and 2 to give 3. 1 and 1/4, and 0 is 1 and 1/4. All right, and then we would go over and plot those points. Now, another technique is to do this, is to graph this and graph that as separate graphs, and then add y values. Let me show you what I'm talking about. I have constructed the graph of those two right here. Can you pick out which is which? I'm sure you can. All right, this is the graph of x over 2, and this is the graph of that cosine curve. All right, it's actually 2 cosine pi x. All right, here's that curve. Now, the way that we generate points for the sum of these two is to add vertical distances at every point on the graph. For example, we could take a point like, I think a convenient point is this one right here at 5. When x is 5, this graph has a y value that is -1, 2. So this is at -2. Now, I'm reading over, now notice that let's not get confused here. On my y-axis, every other mark is a full unit. So this is 1, even though there's a mark here at 1/2, you see. So this is 1, 2, 3, 4, and then the same way going down, same way left and right. Okay, so here we have negative 2. But on the other graph, we have 1, 2, 2.5. So we have 2.5 with negative 2. 2.5 with negative 2. Oh, that's a half when we add those two together. So 1/2, that's right here, is going to be on the graph of the sum of these two. You see, and that's how we make this analysis on and on and on. At this point, and the intercepts are really easy here because we have 0 on this graph, and then we're adding that amount, you see this vertical distance, for this other graph, and so the point will be right on that graph. All right, and then at 6, we have, let's see, we have 1, 2, and then also 3. So 2 plus 3 is 5, and so I come up here at 5, and this point is on the graph. And now we have the kind of thing where we've got this going on. Now I'm sure that this is well, I shouldn't say I'm sure. I'm pretty sure this is a relative minimum point because I have a relative minimum point on one of the items that I'm adding. You see, that's a relative minimum point. And if I come back in this direction, I'm subtracting a little bit less in value here than I have right up here. So I think this graph is going to go up like this. In a similar way over here, if I have two tops, if I have a top here and an item on this graph, I have a relative top here because then I start to turn down. Now, this may not be an actual relative maximum point, but it sure is in the neighborhood, you see, because that graph is going to turn down. And then at this point, at the intercept, I'm back at adding 0 with this vertical distance to give that point on the graph. And here we go with that point. You see, so it behaves like this. And then doing that all along the way, we discover the behavior of the graph of the sum of these two. Well, still, a little bit of a rigorous kind of thing to discover the behavior of that big graph. The easiest way, of course, is to put this on the graphing calculator, and that's what we want to do now. Let's look at it on the graphing calculator, and we're also going to look at the graphs of some other rather exotic-looking equations on the calculator as well. The two equations have been entered, and separately on standard settings, their graphs look like this. Now, upon adding the two functions, however, that is x over 2 plus 2 cosine pi x, we have this effect. And notice it kind of looks like we are causing this cosine curve to take on a rather linear pattern. And that is fundamentally what happens when we add two functions like this. And we can see the situation perhaps more clearly if we take out these first two and just look at the third. Whoops, take out these first two and look at the third. You see the cosine curve is sort of taking on a kind of a linear-like pattern because we're adding the two together. Now, this is not something that's terribly foreign to us. We have seen this situation in the past. That is, remember, when we had something like, oh, I could take y equals 3, I could take y equals sine x, and separately, their graphs look like this. But then if I add the two together, if I take 3 plus sine x, then it almost looks like I'm taking the sine curve and putting it right on top of that line. You see, that is effectively what's happening when I add the two together. Now, generally, we don't see these two graphs. We just see this graph, you see, but actually what's happening is that we're putting sort of one on top of the other. All right, let's do something a little more exotic. Let's clear this one and use another kind of pattern. Instead of fitting a linear pattern of sorts, let's fit something that's curvy. How about x squared divided by 8 and we want to fit onto that sine 2x. Now, let's change our window settings a little bit. I've looked at this before, so I know that something like an x of -6 for the minimum and 6 for the max will look a little better, and we'll change the y to a y min of -1 and a y max of 5. And now the two graphs separately look like this. Here's our parabolic graph, and here is the curved graph. What we're going to try to do is make the sine pattern turn out to be parabolic in nature, and we can do that rather easily by adding the two functions together. Now, there is another way to add the two functions. We can of course enter x squared over 8 plus sine 2x, but another way to do that is to press the vars button and then cursor to the right for y vars, and we want a function, and the function we want is y1, so I'll press enter here, and now I want to add y2, and I go through the little sequence again: vars, cursor right, function, enter, and then cursor down to y2, and now I have y1 plus y2. And now the three graphs, the third graph will come on top of the other two. So we're making that sine curve take on a parabolic pattern. And if we'd like to see this without the other two graphs, I'm not going to clear these because y3 is defined in terms of the other two, but I can press enter with the icon over the equal sign and deselect these two for graphing. So the graph of the third one will come up alone. The sine curve in a kind of parabolic pattern. Well, here's another. Let's get away from this idea of adding functions, and let's consider what happens if we multiply functions. It turns out that we can define the borders of a graph and make a sine or cosine pattern go into a certain border. Let me show you what I'm talking about here. Suppose I enter 3 and -3, something very basic, and then we know what the sine curve looks like, but I'll enter it anyway, and we'll take a look at these. And I think I'd like to have a look at these in a different window setting. This is okay for x, but I want plus and minus 4, I think, for the y's, and the graphs then look like this. Okay, these are all the expected outcomes, but in order for me to cause this sine curve to go up to this mark and down to this mark, make this the top of the amplitude and this the bottom of the amplitude, all I have to do is multiply them together. And we've seen it a number of times before. This would then be 3 sine x. And let me take off the regular sine curve here so we can see this more clearly. But here is the graph. So by multiplying the two functions together, we are defining or describing a border sort of for our sine curve, and then we're placing that sine curve within a particular border. Now we can make that border look as exotic as we would like for it to look. Let's clear this one off and come up with a rather exotic looking border. How about a border that is something like 1 over x and the negative of 1 over x. And so here's the border. And I'm going to change window settings. We'll look at the border in just a second. I'm going to make up my window settings x min -12 and the max 12. And then I'll come down for the y's and set the y at -0.5 and the max at 1.25. Kind of tight on the y's, but you'll see why in a minute. And these two graphs are here. Now, what I'm going to try to do is get a sine curve to wiggle in between these borders. And I can do that by doing this. Just enter 1 over x times sine x. Now, I would like to make this a distinct coefficient, so I'm going to go back here and I'm going to put a parenthesis around the 1 over x. I'm pressing second and insert because I want to insert an open parenthesis here, and I'll close that parenthesis on the other side. And now sine x. So all I'm doing is multiplying the 1 over x times sine x, and I am effectively putting that sine curve inside this border. This is called a damping effect. A damping effect. You know, obviously I could take the border lines off, but it kind of looks neat to see those border lines. Now remember, all I'm doing in multiplying here, remember that a coefficient of sine x is sort of defining the amplitude, and this is the amplitude of that function, and so it goes up to that mark and down to the bottom of that the reflection of that mark, and so on, and just back and forth, just bounces back and forth between that kind of graph, plus and minus that amount. And here's another one. Let's look at one more. This is the most exotic of all. This is my favorite. I'll clear these off. And my border is going to be 1.3 to the x power and negative 1.3 to the x power. And for window settings, I'm going to reset x minimum to be negative 3 and the max to be 10. And then for y, I want plus or minus 8. So negative 8 and 8. And here's the graph of the border that I'm going to create for a sine curve. I'm just going to place a certain sine curve right into this pattern, right in the middle of this pattern. Now all I need to do is multiply, use this function you see as a coefficient. So I will write 1.3 to the x power times, once again I forgot that to confine this within parentheses. So I'll go back and insert a parenthesis here and here. And then now I want this sine curve to be kind of wiggly, so I'll make it sine 3x. And here's the graph. So some rather exotic situations can occur here by using this damping effect. You might play around with this on your calculator and see what kind of different things you can come up with.